Welcome back, everyone, to the new academic year. Our first colloquium of the year and the first on Zoom at NYU is at this unusual time, Friday at 11 a.m., to accommodate speakers outside of the United States. Next week, we will go back to the normal time of Thursdays at 4 p.m., but we will have several colloquia at this particular time and day of the week, allowing us to hear from eminent European and Asian scientists, including our distinguished speaker of today. So today we are honored to have Yifang Wang speak to us. Yifang earned his bachelor's degree in physics from Nanjing University, after which he came to Europe to work under Samuel Ting at the L3 experiment of the LEPI plus E minus collider, eventually earning his PhD from the University of Florence in 1991. He was subsequently a researcher at MIT and Stanford before returning back to China in 2001 for a professorship at the Institute of High Energy Physics, or IHEP, in Beijing, where he is still to this day. Yifang is best known to many of us for his work and leadership in two experiments, the first one being the Daya Bay reactor neutrino experiment, which was the world's first, which made the world's first determination of the so-called theta 1-3 mixing angle, one of the last few unmeasured parameters in the standard model before that experiment. And the second being the Beijing spectrometer, the third version of it, currently at the Beijing Electron-Positron collider, which conducts precision studies of the tau lepton and the charm quark and associated composite hadrons. So these two experiments are springboards for future state-of-the-art facilities envisioned and led by Yifang, namely the Jiangmen Underground Neutrino Observatory, or JUNO, and the Circular Electron-Positron Collider, or CEPC, which could be upgraded to the world's highest energy proton-proton collider. Perhaps more influentially, in 2011, Yifang became director of IHEP, which houses not only the experiments that I just mentioned, but also an expansive portfolio of other experiments, including on dark matter and ultra-high energy cosmic rays, to name just a few. So today, Yifang will give us a bird's eye overview of this rapidly growing Chinese high energy physics program. Needless to say, Yifang has won many awards over the course of his career. I'll name just two, which are the Panofsky Prize in 2014 and the prestigious Breakthrough Prize in Fundamental Physics in 2016. Some Zoom logistical details before I give the virtual floor to Yifang. So we encourage everyone to engage with the speaker and ask questions. All of you are muted at the moment, but you can unmute yourself at any time to ask a question. We hope to stimulate a lively discussion as usual at NYU, but please be respectful of Yifang's time. You can also use your raise hand functionality in Zoom under participants if you want to ask a question, and then I can interrupt the speaker. And for non-urgent questions, you can type your question in the chat and it will be answered at the end of the talk. Yifang, you can start your screen share and your talk, and I'll start recording. Thank you.
Okay, can you see my screen?
Yes.
Okay. Thanks for the invitation. It's a great pleasure, and also sorry for the very unusual time for all of you, and particularly for students, which may be too early. So I will try to summarize what we have been doing up to now, and also what is our plan for the future. Before we go on, I'd like to give you a little bit of a summary or review of the history of particle physics in China. So first of all, the accelerators indeed, there were a number of small accelerators starting from 50s. And you can see here the 2.5 MeV proton accelerators and all the way up to the LINAC. And indeed, there were a number of large high energy physics accelerators proposed starting from 60s all the way up to 80s, and they all failed until the real start, the Beijing Electron-Positron Collider, sometimes we call it BEPC. So BEPC is actually the real start of high energy physics in China. It has three components. So one is Beijing Electron-Positron Collider, we call it BEPC. And then the detector, we call it Beijing Spectrometer, BESS. And also a synchrotron radiation facility, we call it BSRF. So this is a machine for two purposes, the particle physics and also synchrotron radiation. The beam energy, or not beam energy, the central mass of energy is from 2 to 5 GeV, and the construction started in the year of 2084, and the first collision started in 1988. So after 20 years of, almost 20 years of operation, we went through a major upgrade called the BEPC2 and BESIII. And this upgrade actually ended up a completely new detector, we call it BESIII, and also a two-ring electron-positron collider. So you can see from this picture, this is a completely new technology. And from top right, you can see that the luminosity of this machine had been, in fact, quite advanced at the time when it was the firstly designed and built. And then afterwards, we had the CSIR-C, which was actually exceeding the luminosity of BEPC. And then the BEPC2 had this increase of the luminosity by almost factor of 100. And we are now still the highest luminosity machine in the tau charm energy range. So this is some pictures of detector construction. You can see this is a drift chamber, cesium iodide crystal calorimeter, and also superconducting magnet in the muon chambers. And you can see that most of our team are actually here in this picture. So BESIII is actually quite large international collaboration. We have 16 European groups, 5 from the US, and of course, majority is from China, 45 institutions, plus a few in Asia. The main physics topics in this machine and also the detector is the following. First of all, the Hadron spectroscopy and also exotic Hadron searches. And then the Charmonium production decays, including the famous XYZ particles. And also we are doing very precision measurements of R values, the form factors, the tau mass, CKM matrix elements, and so on. So you can see from this picture, we have a very complicated resonance structure, and there are actually a lot of new physics in this energy range. Most of the physics topics...
Это хрю настоящее. Пойди посмотри копытца.
So, okay, can you hear me? Yes.
Yes.
Okay. So from this picture, you can see the structure, complicated structure of resonances in this 3 to 5 GeV, and most of the physics topic has been summarized in this review articles in International Journal of Modern Physics. Up to now, after more than 10 years of data taking, we have collected 10 billion JEP size, 0.5 billion psi prime, and 3 inverse femtobar psi double primes, and then another roughly 25 inverse femtobar of data from 3.7 GeV to 4.9 GeV. Up to now, we published roughly 260 papers by the collaboration, and typically we have 20 to 30 papers per year. We plan to operate this machine and the detector up to 2030 with a planned upgrade in the next few years. And we would like to increase the luminosity by another factor of 3. So that was the plan before 2025. A few very key, say, important physics results we obtained from this machine and the detector. The first one is the ZC3900 discovery, and this is a resonance made of pi and gypside. So this is actually very clear 4 quark states made of UD and the CC bar. And afterwards, we observed their companion particles, like excited ZC3900, higher mass, made of pi H sub c. And also we have the neutral particles like ZC3900 neutral. I didn't have the plot here, but also I have this 4020 neutral particles observed, made of pi 0 H sub c. So these are all very interesting particles. They could be the long sought multi-quark states like moleculars, tetraquarks, or maybe hydro charmonium. So it's not very clear which one is the one we discovered. We need more data to understand the details. Of course, there are also suggestions that what we have been seeing are just the threshold effects, so-called the cusp. We certainly try to collect more data with the partial wave analysis and also the indication of the lattice QCD to understand the details and understand nature of these particles. That's why we need more luminosity and more data in this energy range. So these results actually have been very well covered by the media like Nature and the physics world. We also discovered many other new particles and also interesting new processes. For example, X1870, you see this peak here by the eta pi plus pi minus. We also see a very interesting global candidate X203070 made of pi pi eta prime. And also we observed for the first time the decay, the process of or decay of Y4260 to gamma X3872. We also realized that the famous Y4260 is actually a complex structure. There is another structure here at a mass of 4360. So indeed, this is 2 particles in a previous known as the Y4260. So I mean, many of these kind of interesting results have been obtained from this machine and the detector. So we would like to continue to take the data and analyze them in a great detail. So next step is a Higgs factory. Indeed, since 2005, when we just finished our BEPC, we were discussing what is a possible machine for us in the future. And the idea, actually, we discussed it for many years, and the idea of a circular E plus minus collider, we call CEPC, followed by a super proton-proton collider, we call the SPPC, was proposed in September 2012. And this proposal quickly gained the momentum in IHEP, in our institute, and in China, and also in the world. So the idea is to look for hints of new physics at the E plus minus collider. And if yes, then we can go to direct searches at the PP collider. So the kernel of these 100 kilometers can house firstly a E plus minus collider, just like LAP. And then you can put a proton-proton collider or maybe ion-ion collider into the same kernel. for all the way up to 100 TeV energy. So indeed, we have to study the compatibility of the two machines in the same terminal. That's why we were talking about CEPC and SPPC together. But indeed, what we have in mind is to build CEPC at this moment. And the SPPC is not something at highest priority. So the reason we would like to put Higgs as the first priority is the following. Higgs is actually a window to the new physics. First of all, Higgs is a very special particle. It is the only one which has a spin zero, and people can easily question whether Higgs is elementary particles or not. It is very similar to pi, and even more similar to Cooper pair. And the Higgs potential has exactly the same shape as a Landau-Ginzburg potential model. And these equal shape of the potential may indicate that Higgs itself could have also a very similar nature as a Cooper pair. In addition, Higgs is the only elementary particle which has the non-gauge interactions. There are a lot of issues related to physics beyond the standard model and the cosmology. For example, the Higgs give the mass to all the particles, but we don't know where the origin of the Higgs mass itself comes from. And also, we don't understand why the vacuum is metastable. And this is determined by the value of the Higgs mass itself together with the top quark mass. So the top quark mass and the Higgs mass put our vacuum in a metastable region. So this is very strange. And also Higgs is giving the mass to all the particles. We certainly have a question whether Higgs gives the mass to the dark matter or not. And certainly they should couple to the dark matter because they all have the mass or gravitational interactions. And the Higgs potential shape should determine the electroweak phase transition. And this shape of the phase transition actually determines the evolution of the universe. So indeed, we would like to have a detailed and precise measurement of the Higgs to understand its properties and to understand these issues related to the new physics and also the cosmology. Indeed, what we try to measure is a coupling of the Higgs to all the known particles and try to look for the deviation from the standard model. So for example, at LHC, we have direct searches of new particles and we didn't see any. So the mass scale of the new particles has been set to at something like around 1 TeV. And we are able to measure the couplings at the level of 10%. And this gives you also an energy scale very close to around 1 TeV. The purpose of the CEPC is trying to measure the couplings of Higgs with all the particles at the level of 1%. And the 1% precision, of course, related to the new physics scale at the level of 10 TeV. So Higgs factory or CEPC actually is very probable or could be very probable to find a new physics. The reason is the following. If you look at the mass of Higgs, it's a subtraction of the two large numbers. And if the new physics is at 1 TeV, then these two numbers have to be equal at the level of 10 to minus 2. And if the new physics is at 10 TeV, then these two numbers have to be equal at 10 to minus 4. If we have no new physics all the way up to the Planck scale, 10 to 16 TeV, then we ended up this 10 to minus 34, this mass of the Higgs by two huge large numbers subtraction. So from this, you can imagine that 10 to minus 4 or 10 TeV is a very probable new physics scale for us. So we think that being able to reach the level of 10 TeV for new physics is a milestone, extremely important. For the Electroweak phase transition, up to now, we only know the Higgs potential shape at a very small corner, like this right figure. But the potential can be the first order or second order, just like this red or green curve demonstrated. So the difference of this the first order or second order or the green or red curve have very different or very major consequences to the universe evolution. So we would be very much like to know which one is correct. And by measuring the self-coupling of the Higgs, we are able to determine the shape of this Higgs potential. This is a very important outcome of the study of the Higgs potential, Higgs properties. A machine like a circular collider can easily run at different energy, not only at the Higgs, but also at the Z. So we are able to have this roughly 10 to 12 Zs from this machine by 1 or 2 years of running. So we can have a very detailed study of the Z and the W to look for deviations from standard model. So a combination of the study of the deviation from a standard model by Z and the Higgs and W can give us a hint of the new physics. And indeed, such a Z factory it has a precision much better than the high lumen HC by almost factor of 3. So the machine is designed as following. So we have a collider ring and then a booster, and then we have an injector as shown at the bottom. So the design luminosity is 5 times 10 to 34 for the Higgs, 14 times 10 to 34 for the W, and then for TT bar and the Z. The baseline is 100 kilometers, 30 megawatt per beam for the synchrotron radiation. And of course, it is upgradable to 50 megawatt, and also for high lumen Z, and also for the TT bar. Indeed, we try to have a minimum version of this machine to cut the cost down, or cut the initial cost down. So we have been working on the Accelerator R&D in the last 5 years, including the polarized electron gun, the positron source, RF cavities, klystrons, magnet, vacuum pipes, and so on. So and we got some results in the last 5 years. So first of all is the RF cavities. So we have 2 versions. One is the baseline, it's a 650 megahertz 2-cell cavity made of fine grain, the fine grain niobium. And you can see the target vertical test for the Q0 is 5 times 10 to the 10. And we already made several cavities, and they have been tested okay. Another option is the 1-cell cavity made of large grain, and this could give us a higher luminosity for the Z, and also cheaper and easier. But it's more difficult. You can see that the target is for the Q value is 5 times 10 to the 10 at 42 megawatt per meter. So this is a much bigger, much difficult kind of a task. And we managed to make 4 cavities and still under testing. The result is not satisfactory. We haven't yet reached the level of 42 megawatt per meter, but close, so 30 something. So we try still to improve this. And also we have been made 1.3 gigahertz 9-cell cavities for the booster. And this is same as Shanghai light source and also international linear collider. So we have to make these kind of cavities anyway. So this is actually, we made several cavities already successful and reached the specification. Indeed, the most difficult part of the cavity is the mass production. This is actually more difficult, much more difficult than a few prototypes. So thanks to the city government of Beijing, we got the funding support to build a large testing facility as shown in this right figure. So this is a 2-floor building with something like 5,000 square meters. And this is going to allow us to do all the cavity testing and assembly. So the Shanghai Light Source project is supported by the Shanghai city government, and they need something like 400 cavities. We are going to provide more than a third of them. This is actually a very good opportunity for us to exercise our cavity production and the module assembly. And they plan to finish the construction by the year of 2025, so way before the CEPC construction. So we believe that we should be able to get the exercise of the cavity production before the CEPC start. Another R&D example is the high efficiency klystron. So we made our first prototype with efficiency of 64%. This is normal efficiency. Completed and tested successfully. You can see some of the pictures here, and this right figure is the finally completed klystron with 800 kilowatt power and the 64% efficiency. And then we are actually plan for the construction of the second prototype with high efficiency, 80%. And this is what we needed for CEPC, because CEPC has a huge power consumption, and a high efficiency means a much reduced energy consumption. So this is actually a very critical for the CEPC, and we plan to finish this R&D before the start of the construction. Of course, technology can be used for any of the future electron machines or microwave power supply. A third example is the plasma injector. Unlike other, say, international large accelerator labs like CERN, they have a lot of smaller accelerators to be used for the injector. And we are trying to build this new CEPC machine from Greenland, which means that we had to build everything from scratch. So injector, we had to build also from scratch, and this is very costly. So we hope that we can use the plasma technology to build this injector so that we can save energy. For example, if you see from this picture, you can see that from 10 GeV to 45 GeV, we just need a very small stage of a plasma weak field acceleration unit. And this can actually increase dramatically the energy to be injected into the booster and save us a lot of cost. So if this is successful, it's going to be the first of its kind for a real accelerator, say, component. So we actually finished the design, and we are going to do a few further tests, particularly a plasma acceleration test for electrons at Shanghai soft X-ray, free electron X-ray facility. And also we had to do a test for positrons in FASET at the SLAC. The last one is the ion-based superconducting magnet. We all know that for the future proton machines, magnet is a key technology we have to control and being able to reduce the cost. So this picture shows you all the possible materials to be used for the cables of superconducting magnet. The famous niobium titanium is going to drop, is actually dropping their current limit up to something like, let's say, 10 TeV. So you are not able to build anything more than 10, sorry, not 10 TeV, 10 Tesla. You are not able to build any magnet based on niobium titanium to the level of 10 Tesla. And for niobium tin, you can go all the way up to something like 16 or 14 Tesla. Here you can see it dropping. And so the future actually relies on very much on the high TC superconducting materials like this one, Repico. But the Repico has a very strange property. The current limit in parallel to the field and the perpendicular to the field are different. So they have a huge difference here. And this makes us very difficult to build a magnet made of Repico. Another candidate is the bismuth 2212. But bismuth 2212 is very expensive, and you cannot imagine that we are able to build our huge number of magnets made of these expensive materials. So iron-based superconducting materials is a hope for the future. This is what we are able to achieve right now in 2016 in China by the Institute of Electric Engineering. And over 3 years' effort, we have been working with them. We managed to increase the current limit to by almost a factor of 3. So this is our target. So we hope that by the year of 2025, we should be able to reach this level as the bismuth 2212, and then we should be able to build our future proton collider magnet using the iron-based superconducting material. So we are actually working on this, and we also got funding from Chinese Academy of Sciences to develop these kind of new technologies. And we believe that this is not only important for the high-energy physics, but also if we are successful, this is also going to be very useful for the for other field, industry, and also society. This picture, the left bottom, shows you a test of the world first iron-based superconducting coil under a very high background field of 20 to 25 Tesla. So you can see that iron-based superconducting coil does not drop very much their current in a very high field. It's the first demonstration that iron-based coil should be able to be used in a very high magnetic field. So this is a proven of the technology. So now let me talk about other activities in China, say cosmic ray physics, space experiments, and also underground experiments. So let's first talk about underground experiments, Daya Bay. In the year of 1998, Super Kamiokande experiment observed for the first time atmospheric neutrino oscillation and managed to measure the mixing angle theta 23. And then in the year of 2001, SNOW experiment observed the solar neutrino oscillation and measured the mixing angle theta 12. So of course, in the year of 2021, 2022, people have a very natural question: what is the angle theta 13, and what is the value, whether this kind of oscillation exists or not? Before 2001, there were 2 experiments trying to look for theta 13. This is Paloveda and the Shoes, and they didn't see any signature of the signal of the neutrino oscillation, and they set a limit. And combined with the limit of the Super Kamiokande, this red region is the allowed region for the theta 13. So this is the situation in the year of 2002 or 2003. We try to determine theta 13 in this red region, parameter space. And the desired sensitivity is 0.01 compared to the previous sensitivity of 0.1. You can see that there's a factor of 10 improvement needed for the next generation CETA-13 experiment. So we proposed in China to build our detector in the Daya Bay reactor complex, where you have 6 reactor, 60 reactors, Daya Bay, Lingao, and Lingao 2. So we designed our arrangement of the detector in 3 locations, 2 near detector nearby the reactors, and then 1 experimental hole as a far detector. By having this near-far arrangement, we are able to cancel the correlated uncertainties. And then in each experimental hole, we have multiple detectors. In the near detector, we have 2. For the far detector, we have 4. By having this kind of multiple detector modules, we are able to reduce the uncorrelated systematic uncertainties. Indeed, it is proportional to the 1 over square of the number of modules. So 4 modules means you reduce the uncertainty by a factor of 2. One of the biggest challenges for the Daya Bay experiment is the liquid scintillator, in particularly the gadolinium loaded liquid scintillator. There were a lot of issues in the past because both the SHUS experiment and the Paloveta experiment experienced difficulties with the transparency in the agent, and they actually see very quickly degradation of the transparency of the liquid scintillator. So now we had to build a very large quantity, 180 tons of gadolinium loaded liquid scintillator, and we had to find a new formula. You can see from the right bottom the tables, so the different technologies, SHUS, Paloveta, double SHUS, and Daya Bay. We all use, you see, we have very different technologies and also different gadolinium compound and a very different total quantity. I mean, we need almost factor of 10 more this kind of liquid scintillator. So in the end, we managed to solve the problem to invent this new formula and came up with the world's best transparent liquid scintillator. Attenuation length is roughly 15 meters. And also we got the liquid very stable and better than 1% per year. So finally, with this liquid scintillator and with our detector, by taking the data in 3 months, we managed to see the disappearance of the electron antineutrino from the reactor. And the level of this disappearance is about 6%. And this 6% of the disappearance of reactor neutrinos corresponding to a CETA-13 or sine squared 2 CETA-13 to 0.092. So this is actually the amplitude of the oscillation. And this corresponding to 5.2 sigma, the statistical significance for non-zero CETA-13. So this was in the year of 2012. And over the last 8 years, we managed to improve this precision all the way down to the level of about 3.4% from 20%. And you can see that the result of Daya Bay comparing to Reno in Korea and the double SHUS in France, you can see our precision is actually very much dominant. And we plan to stop the data taking of the Daya Bay by end of this year, actually December 12th of this year, and the expected precision for the sine squared 2 CETA-13 and the delta m square is less than 3%, something like 2.8, 2.7%. So this is Daya Bay Collaboration. We have quite a bit of the US contributions. Indeed, roughly 1/3 of funding from the DOE. So there is a very large contributions from the US. And also, of course, other countries like Russia and the Czech Republic. So indeed, starting from 2008, we were actually thinking about what's next after the Daya Bay experiment. And after a few years of study, we concluded that we need to concentrate on react neutrino experiments, and we should utilize our expertise on the liquid scintillator. So we came up with the idea to put a detector in the oscillation maximum of theta 1, 2. And by having large enough detector to measure precisely the energy spectrum from reactors, we can determine neutrino mass hierarchy. So this was the idea, and we managed to find a place in China, not very far from Daya Bay, 2 reactor complex. So each of them is equal to the Daya Bay complex. So having these 2 reactor complex, which has a distance of something like almost 100 kilometers, we are able to reduce the detector size, and the equal distance of 50 to 60 kilometers, we are actually fortunate to find a small mountain there, and we can build underground laboratory. The physics at JUNO is the following. First of all, for 6 years, we are able to measure the mass ordering at the level 4 sigma, independent of CP phase. And also we can measure the neutrino mixing parameters to a precision better than 1%. You can see from this table, right bottom, we are able to improve the precision by almost factor of 10. And indeed, the precision of neutrino mixing parameters is going to be better than quark sector. And I think a quark sector, after so many factories like B factory, C factories, and 5 factory, we only managed to reach something like 1% level. And here we are able to, by 1 experiment, go all the way down to a sub 1% level. And if we have a supernova burst, we should be able to see 5,000 events at 1 kpc distance. And we have also potential to find diffuse supernova neutrinos if the average energy of the neutrinos is more than 15 MeV. We should be able to see geoneutrinos, solar neutrinos, and also proton decays.
Yifang,
So, yes.
Will you be able to measure the CP violating angle in the neutrino sector as well?
No, we cannot. You see, we are independent of CT. That means we have no sensitivity at all. So the detector is designed as the following. We need 20 kilotons of the liquid scintillator, which is a factor of 20 larger than ChemLand, or factor 40 larger than Boltzino. But we also need the light yield, which is a factor of 2 higher than Boltzino, a factor of 5 higher than ChemLand, because usually the larger detector, the less the light you are able to collect. So having a factor of 20 larger detector, a factor of times more the light is a very challenging task. You can see this is a size of a detector in a water pool of 45 meters of depth. And the acrylic tank itself is 35 meters in underground cavern of 40 meters, 50 meters diameter and 70 meters height. The most difficult part is the liquid scintillator, which we have to increase the attenuation length by another factor of 2, so 25 meters of attenuation length. And then we need 20,000 20-inch photo tubes with efficiency for the photon detection at the level of 30%, which is roughly factor 2 higher than Super K. So when we designed this in the year of 2020, in the 2008, there's no such photo tube exist. So that was a huge challenge for us to develop this kind of photo tube. The JUNO is again a very large international collaboration. We have 17 countries. and the 77 institutions with more than 600 members. So we are actually working on the detector R&D and the construction in the last 8 years. First of all, we had to build a huge acrylic tank. We designed finally, after many years of study, we decided to build this acrylic tank by 8-meter times 3-meter sheets. Thickness is 12 centimeters. So in total, we need 250 panels or sheets of this kind of acrylic. Then we thermopressing them and make them the spheric shape, and then bond them into a sphere. During the process, we have to make sure that there's no stress more than 3.5 megapascal anywhere. And we had to worry about the bonding, annealing, aging, creeping, creasing, radio purity, precision, and so on. So these are all technical difficulties we have to overcome. And indeed, in the last 5 years, we solved all the problems and the production is almost finished. We actually have a plan to start the installation next year. And secondly, we have this huge stainless steel structure to hold the acrylic tank and also to mount all the PMTs. The PMTs have a clearance among them of something like 3 millimeters. So this is huge, difficult requirement to the precision of the structure and also to the stiffness of the structure. And then we are not able to do the welding, so we have to use screws. So in total, we have 140,000 screws. We need to have a proper clearance, because if a clearance is too small, the screw cannot go through. If the clearance is too big, we're not able to maintain the precision. And then we have the temperature difference between acrylic temperature expansion coefficient difference between the acrylic and the steel. So we have to control the temperature at a constant 21 degree. And we have to worry about earthquake, liquid solid coupling, radio purity, and so on. For the acrylic, liquid scintillator, we managed to optimize light yield and the transparency, and also we had to worry about the purification process itself and also equipment for the attenuation lens and also radio purity. For the phototube, we started in the year of 2008 to develop a new type of PMT to have higher photon detection efficiency with the industry. The company is called the NNVC. We came up with the idea to use microchannel plate instead of dynode to increase the detection efficiency, and indeed this is working. And also we realized that MCPs actually make the mass production easier. So after roughly 5 years of no, more than 8 years of development, starting from 2008, we managed to come up with prototypes which has efficiency more than 30% and roughly 10% higher than Hamamatsu. Indeed, during these 8 years, Hamamatsu increased their quantum efficiency from 25% or 20 to 25% to 30%. So they also managed to increase and their detection efficiency, and their collection efficiency is also increased from 60% to 90%. So indeed, everybody managed to increase their efficiency, and we actually ended up to better than 30%, higher than Hamamatsu. And the performance is actually better with our phototube on the detection efficiency, peak to valley ratio, after pulse, and so on. But dyno PPC has the better TTS. So based on the performance, cost, the risk, and so on, we decided to purchase 15,000 phototubes from NNVC and 5,000 from Hamamatsu. So the combination gave us the best performance and also the best cost. So this plot shows you the increase of the quantum efficiency of the phototubes from NNVT during the production process. So they are continuing to improve their efficiency. And the left corner, corner plot shows you the peak to valley ratio, which is actually very, very good. Peak to valley ratio is almost 6 to 7. This is the civil construction. We need to build underground laboratory with an overburden of 600 meters. So we decided to build a slope tunnel, 1.3 kilometers, and then a vertical shaft of 600 meters. So we have 2 access route so that we are able to maintain the safety of the underground laboratory. So this is the shape. The left bottom shows you the shape of the underground laboratory with the access tunnel. And we almost finished the civil construction. And by end of the year, we should be finished everything. This shows you a picture of a few months ago, the underground cavern. So the dome has been finished. The most difficult, dangerous part of this dome, we at 50 meters span of the dome is safe and over many years. So this actually was the most worrisome part of the civil construction. Indeed, JUNO detector can be upgraded in the future for double beta decay experiment. Indeed, we believe that in 10 years from now, oscillation will be mostly finished. Both the mass hierarchy and also the CP phase will be measured by many experiments. And neutrino-less double beta decay will be the next breakthrough. So from cosmology, we know that the neutrino mass should be less than 1 eV. And from oscillation, we guess that the neutrino mass should be around 1 milli eV. But Cavern can give us only up to level 0.2 eV. So the real measurement can only come from the neutrino-less double beta decay if we have a target of effective neutrino double decay mass of level of 1 milli eV. So up to now, Cavern and Zen and the EXO reached level of 50 milli eV, and the future experiment can go all the way down to 10 milli eV, and JUNO should go to a few milli eV. So we believe that if we finished our mass hierarchy measurement, we can insert a balloon filled with liquid scintillator loaded with either xenon or tellurium. We should able to get a target mass of a few hundred tons, and then we should be able to get to this kind of level of the effective mass of the double beta decays. In addition to neutrino physics, in China we have a Jinpin underground laboratory for dark matter searches, and also for the double beta decays. So there are 2 experiments. One is xenon based, one is germanium based. So they have been actually working on the dark matter searches. And in the future, they have a plan for also double beta decays. So this is the upgraded underground laboratory, which has actually a huge space for housing future experiments. Indeed, a detailed study of future experiment has not yet been come out. So I think we still have to wait a few years to see what is the exactly design of the detector. So for the cosmic ray physics, indeed, this is a starting point for the experimental physics in China. In 60s, we had a Yunnan Cosmic Ray Observatory at a height of 3,200 meters. And then in 70s, we had an experimental site at Tibet, 5,500 meters. And then in 90s, we have experiment in Tibet again, but a different height, 4,200 meters. And we got quite a number of very important results. Starting from, say, 4 years ago, we had this construction of the large high altitude air shower observatory called the LHAASO. This is actually a very large air shower array for cosmic rays and the gamma astronomy. You see from the right picture, the sensitivity of LHAASO comparing to CTA. So this right bottom corner, this is LHAASO, and then this magenta kind of color is the CTA. So at very high energy, LHAASO is much better than CTA, and the low energy, of course, CTA is better. But CTA is a pointing device, and LHAASO is air shower detector. So they are very different because LHAASO can look at the sky all the time and can study the time variant and the extended sources, and also can give a fast indication to CTA. So actually, they are very much complementary. And the construction of LHAASO has been finished at half, and the data taking has been started since last year, and we already got very good results, and it's going to be released in a matter of weeks or maybe a month. Very interesting results. For space program, indeed, we started some of the activities in 80s and 90s. So these are the balloons, some gamma detectors in space, and also a polar detector on board of China's test module of the manned space station, and also some moon exploration program in 2010s. Right now, there are 2 satellites on orbit for science from China. One is a hard X-ray modulated telescope called HSMT. This was launched in 2017, and the payload is actually designed and manufactured by IHEP. There's another satellite for cosmic rays and gamma ray detection, mostly for dark matter searches. And this was launched in December 2015 and was managed and designed by Purple Mountain Astronomy Observatory. For the future, IHEP would like to build a cosmic ray detector on board of the China's space station. The purpose, the science is the following. First of all, we like to look for dark matter from gamma rays from 100 GeV to all the way up to 10,000 GeV. And we can also study gamma ray astronomy and GRBs, microquasars, and so on. And also we can measure very precisely the spectral and the composition of cosmic rays between 300 GeV to PeV. And indeed, they are very much complementary to LHAASO because we can have a direct measured composition in the spectrum in space compared with what have been measured in LHAASO at, say, hundreds of TeV all the way up to PeV. So this is going to be a direct comparison and the cross calibration. So this is a project with international participation from Italy, Switzerland, Sweden, and so on. And we hope we can launch it in the year of 2025. So the speciality of this detector is following. It is made of small cubic LYSO crystals. So by having this kind of 3D crystal calorimeter, you can actually have a very good energy resolution and also pattern recognition capabilities. And also you can look at the sky from 5 different directions. They're all equal. So in this case, you can increase the acceptance by easily a factor of 5. And indeed, we have acceptance which is almost factor of 10 or even 20 larger than previous experiment. For example, comparing to AMS, the acceptance is almost a factor of 30. So this detector design has acceptance and energy range by almost a factor of 10 higher than anybody else. So this is going to be a very interesting detector in space. Finally, we have a so-called upgraded version of HXMT. It's called the EXTP. So this is a next generation X-ray observatory with an effective area of 5 to 10 times larger than the previous telescopes. So this is again international collaboration between China, Europe, and other countries. And we also hope to launch it in the year of 2025. So maybe a bit later. We haven't got the real final official approval. So finally, this is a summary. We have this table, current experiments like a BESIII, international projects, CMS, Atlas, HCB, and so on. And also the Daya Bay followed by JUNO. EXO is the experiment we're actually collaborating with. And in the future, we'd like to join NEXO. And these are the Jinpin underground experiments, cosmic ray experiments, and also space program. So I stop here. Thank you. Any questions?
I have a question about the electron accelerator, the plus and minus. I talked to people at CERN, and they say that even at CERN, they lost the knowledge of how to do the RF, the radio frequency cavities that were used at lab. They don't know how they were done exactly because they didn't. So they have a group that tries to recover knowledge, but some knowledge is there. Do you have an exchange of expertise between, say, CERN or SLAC and your groups on these technical details on how to do radio frequency cavities, etc.? Or is each group going its own way?
I think each group is going on its way. In particular, right now, it's very difficult for us to collaborate with US national labs, so we are not able to exchange any technical details. But in the past, the technologies on these cavities for IRC has been known to almost everybody. So the technology for the future RF cavities are very similar to the IRC. So in our case, for example, the booster use the exact same type of cavities for IRC, and for the main ring, it's just different frequencies. It's also very similar technologies. CERN is very different. CERN has been working on very different type of RF cavities for lab. It's very different technologies. So I think they worked on the Hadron machine. So they don't have this kind of, very good experience on these type of cavities, but they should be able to catch up if they decide to go toward this direction.
I think that Neil
had a question. Yeah, so you have this idea to use the JUNO vessel as some sort of, you're using it like as a veto for the neutrinoless double beta decay experiment. That's basically how it's working?
Yes.
So you're putting a scintillator in the core of it, and then you're using the larger vessel as a veto and a shield?
Yes. Yes.
Is there any discussion about doing something similar like that, but doing somehow doing it as a dark matter experiment, or is it really difficult to do that and it's kind of uniquely set up for this double beta decay purpose?
Yeah, for dark matter, it's very difficult because dark matter, you have to go to a very low threshold. We don't have that kind of, sensitivity to very low energy. And we are only sensitive to the level of, say, several hundred of keV. It's hard for us to go further down.
A separate question then about the theta 1-2 aspects and the mass hierarchy aspects of it. So for Daya Bay, I kind of understand that you have like very different baselines that allow you from the different reactors. So are the baselines sufficiently different here that you can do that, or are you having to really tease that out for the distances from the reactors to JUNO?
It's not important for the mass hierarchy determination. You see that from this picture, the right middle one, the distorted energy spectrum due to the oscillation. And for Daya Bay, we're actually looking a very small difference from the original shape. So you actually worry about not only the shape, but also the absolute scale. Here you see the structure. You have peak, you have valley. So in the end, if you don't have a near detector and your baseline is not very well known, but the structure is still there. So it is not very sensitive. So indeed, we have a near detector to get a reference, but indeed, if you don't have this reference detector, it still works. So we don't need this near-far cancellation.
I think Alan has a question. But you're muted, Alan.
Sorry about that. Can you hear me now?
Yes.
Okay, so I have a question about LHAASO. This goes back to my Milagro days. Milagro had a single large water Cherenkov detector, and then for the Hawk upgrade, they decided for various reasons that it was better to go to individual modules as opposed to one large one. So I was just curious, it looks like for LHAASO, it's one large water detector with screens, and I was wondering if you know what the motivation was for going that way.
To be honest, I'm not the expert of it. LHAASO had 3 water pools. You see the middle, the blue one. So it's 3, one big one and 2 smaller one, which is half of the big one, and they have 3 water pools. They had simulation, and they concluded that this kind of configuration is better, but I can't tell you the details.
Okay, thank you.
Thank you.
Wannes?
Yes.
Hi, that was just a phenomenally wonderful talk and really, really inspiring program. I wondered if you could talk if you could go to the last slide. I wanted to ask you about the planning and the status of the approvals and so on. Naturally, there's a certain amount of envy in my my question.
Right.
And also I wanted you to tell us a little more about the time sequence of the energy in the E+E- collider. But from this, I didn't see CEPC actually in the approved stage, if I'm understanding so are you saying
Yes.
what wasn't clear, that CEPC is already approved, but the upgrade to SPPC is not? I wanted to understand that question. And then maybe you could just tell us a little about the timescales for these things being approved. I mean, the timescales you're talking about are so fast, it's sort of mind-boggling.
You can see this table. All the red colors are not approved. So the white one are approved. So you see JUNO is approved, LHAASO is approved, and then construction, and all the rest are still in red. So CPC was not approved. HERD and the EXTP are not proved yet. So we believe that the HERD and the EXTP will be proved for sure, although we don't know exactly when. But CEPC, we are not sure whether we can get approval in the near future, say within 5 years from now. Of course, SPPC is even far away. This is 30 years from now, so we cannot even talk about it. So right now we are still working on the design, R&D, and so on, and we try to get support from the government for the construction. Up to now, we got funding support for the R&D, but not a promise for the construction.
Mm-hmm. Thanks. Well, if nobody else is interrupting with a question, I'll ask a follow-up, which is what would be like an optimistic timescale for finishing the R&D to the stage it can be approved, and then actually being able to do this ambitious Higgs program you were talking, being able to start that?
We were hoping that we are able to get a final approval, say within 5 years from now. So we think that we should be able to finish the preparation, like design, the civil preparation, the technology R&D, so on, in the next 5 years, and hopefully the government can prove the project within the 5 years from now. Of course, 6, 7 is also okay, but we believe that it doesn't make too much sense if we have to wait, say, more than 10 years, because by then probably ISC will be approved or may start the construction, and other projects may come along like FCC and so on. So by then we probably have to abandon the idea to build CEPC, and we should just have to join, say, FCC or ISC.
And roughly speaking, the turn-on time, if the funding gets approved fast enough?
It's 10 years for the construction. So if 5 years from now for the approval, and then say wait another 10 years for the construction, so it's 15 years from now, so 2035.
Thanks so much.
Plus minus many years.
Okay, I don't see any more questions, so I think we should thank our speaker again for a great first colloquium to start off the year.
Thank you. Thanks for the invitation. It's a great pleasure for me.
Very good.
Thank you so much. That was wonderful.
Thank you.
Thank you.
Yeah. Thank you very much. That was really nice and interesting.
Bye-bye. Thank you. Thank you.
Good night for you.
Good night.